For more than a year, a discarded rocket stage was drifting through space with no engine burn planned to bring it home. Then gravity slowly settled the question of where it would end up. On August 5, 2026, the upper stage of a SpaceX Falcon 9 slammed into the moon at about 5,400 miles per hour. No astronaut was nearby, no lunar base was threatened, and there was no dramatic fireball visible in the sky. But 6 days later, NASA pointed the Lunar Reconnaissance Orbiter toward the impact site and found a brand new scar on the moon. The crater is about 60 feet, or 18 meters, across and less than 10 feet deep. Around it, dark and bright streaks spread across the surface like butterfly wings. Those streaks are more than debris. They reveal different layers of lunar material, including fresh rock and soil excavated from beneath a surface that had been altered by solar wind, cosmic rays, and micrometeorite impacts for immense periods of time. An accidental rocket crash had become a planetary science experiment. The story began on January 15, 2025, when a Falcon 9 launched 2 commercial lunar spacecraft, including Firefly Aerospace's Blue Ghost 1. After completing its job, the upper stage remained in cislunar space instead of returning to Earth. Solar radiation, lunar gravity, and the complicated gravitational environment around Earth and the Moon gradually changed its trajectory. By the summer of 2026, calculations showed that the roughly 4-ton stage was heading directly toward the lunar surface. This was unusual because scientists knew far more about the incoming object than they usually know about a meteoroid. Its approximate mass, shape, trajectory, and impact speed could all be estimated before the collision. That turned the event into a rare natural laboratory. Researchers could predict what the impact should do, then compare those predictions with the actual crater and debris afterward. Before the crash, simulations suggested that the rocket could throw material tens of kilometers above the lunar surface. The central ejecta plume might rise much higher than the surrounding curtain of debris, while particles could spread across a large region around the impact site. Ground-based telescopes and spacecraft prepared to observe the event, although the geometry made it difficult because the impact occurred on the sunlit part of the moon near its limb. The stage hit near Einstein crater at roughly 2.43 kilometers per second. That is extraordinarily fast by human standards, but actually slow compared with many natural objects striking the moon. Meteoroids can arrive at tens of kilometers per second. The Falcon 9 stage therefore created a useful test of a different kind of impact. A large, hollow artificial structure arriving at lower velocity than many asteroids. The collision transformed the rocket's kinetic energy almost instantly. Metal, lunar soil, and rock experienced enormous shock pressures. The stage itself would have been severely fragmented and largely vaporized or melted during the event, while the lunar surface was excavated outward, but nobody immediately had a close-up view of the crater. NASA's Lunar Reconnaissance Orbiter, or LRO, circles the moon from pole to pole roughly once every 2 hours. The moon rotates underneath that orbit, so LRO cannot photograph any location whenever engineers want. It must wait until the spacecraft's path and the target line up. That created a strange 6-day delay. Scientists knew a new crater existed somewhere near their predicted coordinates, but they had to wait for the moon to rotate into the right geometry. Then another spacecraft beat LRO to the scene. South Korea's Danuri Lunar Orbiter photographed the impact region first. Its observations showed a fresh surface disturbance close to NASA's predicted location. The measured position was only about 0.6 miles from the forecast impact point, an impressive result considering the rocket had spent more than a year moving through the complicated gravitational environment between Earth and the Moon. Danuri then passed the refined coordinates to the LRO team. On August 11 and 12, NASA engineers performed a special maneuver, tilting their spacecraft away from its normal orientation so the narrow-angle camera could look directly at the site. The timing had to be extraordinarily precise. LRO was flying about 60 miles above the moon at roughly 1 mile per second. A photograph taken only 10 seconds too early or too late would move the intended target around 10 miles across the image. The camera found it. By comparing the new images with older photographs of the same location, researchers could immediately identify a crater that had not existed before August 5. Images taken from several viewing angles and under different lighting conditions revealed the shape of its rim and the shadow cast inside it, allowing scientists to estimate both width and depth. But the most visually interesting feature was outside the crater. Some ejecta rays appeared dark, others were strikingly bright. The difference reveals what the impact excavated. The moon has almost no atmosphere, liquid water or biological activity to continually refresh its surface. Instead, exposed material is gradually altered by an environment unlike anything on Earth. Solar wind particles bombard individual grains. Galactic cosmic rays pass through them. Tiny meteoroids repeatedly strike the surface, breaking and melting particles over enormous spans of time. This collection of processes is known as space weathering. Material that remains exposed gradually develops different optical properties from material protected underground. When the Falcon 9 stage struck the moon, it effectively drilled through those layers with an explosion. NASA's analysis indicates that some of the darker ejecta came from weathered material extending to around 1.5 feet beneath the surface. The brighter material closer to the crater was excavated from deeper layers that had been protected from long-term exposure. In other words, the collision briefly opened a window into the moon's subsurface. Scientists normally need a lander, rover, or astronaut to physically dig into lunar soil. An impact performs excavation automatically, throwing underground material across the surrounding landscape where orbiting instruments can examine it. This is one reason scientists deliberately crashed spacecraft into the moon in the past. NASA's CROSS mission, for example, intentionally sent an impactor into a permanently shadowed lunar crater in 2009 and studied the plume to search for water and other materials. The Falcon 9 event was different because it was not originally designed as a lunar impact experiment. Its scientific value appeared only after orbital dynamics made the collision unavoidable. That accidental nature created another opportunity, testing how well humanity can track artificial objects moving through cislunar space. The first useful trajectory predictions came partly from independent observers using publicly available information. NASA's Center for Near-Earth Object Studies then refined the expected impact point using techniques related to those applied in planetary defense. Normally, planetary defense means tracking asteroids and comets that could threaten Earth. Here, the target was human-made, and the destination was the moon. But the underlying challenge was familiar. Take imperfect observations of a moving object, predict its future path, then compare that prediction with reality. The crater provided the final answer. NASA's predicted position was accurate to within approximately 1 kilometer. That result matters as the space surrounding the moon becomes increasingly crowded. More nations and private companies are sending orbiters, landers, and rocket stages into cislunar trajectories. Objects that are harmless today could become navigation hazards when permanent infrastructure and crews begin operating there. A discarded upper stage hitting empty lunar terrain is very different from debris intersecting the orbit of a spacecraft or landing near a future surface installation. The event therefore points toward a problem that barely existed during the Apollo era: lunar traffic management. On Earth, much of our orbital debris eventually encounters atmospheric drag and falls back toward the planet. Around the moon, there is essentially no atmosphere to provide the same cleanup mechanism. Objects can remain on complicated trajectories until gravity redirects them. They collide with something, or controllers deliberately remove them. That makes accurate tracking increasingly important. But there is also a scientific advantage to future known impacts. If an old spacecraft must be disposed of on the moon, engineers could potentially choose impact locations that minimize risk while still producing useful scientific data. Known mass and velocity would allow researchers to calibrate crater formation models and study the response of different lunar terrains. The August impact offers an unusually clean example. Scientists predicted the event before it happened. Multiple observatories prepared for it. A spacecraft found the crater within hours. Another photographed it at high resolution days later. Researchers now know the final crater dimensions and can compare them against numerical models built before impact. That makes the new crater more than a hole in lunar soil. It is a controlled data point in a process that normally happened millions or billions of years before anyone could watch. Almost every crater we see on the moon records a collision whose exact conditions have been lost. We can measure the final crater, but usually we do not know precisely how large the impactor was, how fast it moved, or what shape it had. With the Falcon 9 stage, scientists know much more about the object before it hit. That gives them a rare chance to run crater physics backward and forward at the same time. A rocket launched to send spacecraft toward the moon eventually returned to the moon itself. Its mission had ended long before the impact, but its final seconds created a 60-foot crater, uncovered material buried beneath the lunar surface, and tested our ability to predict where an object moving through cislunar space would collide. The moon now carries another human-made scar. But this one arrived with a timestamp, a trajectory, and enough information for scientists to turn an accident into an experiment.